everyone for coming today. It's really great to have all these people together. And I've really enjoyed the discussion sessions. So my name is Maria, and I'm a 5th-year PhD student with Adam. And I mostly work on geochemistry of magnetite applied to the origin of iron oxide, copper, gold deposits, and IOA deposits. And today I'm going to focus on the Mina Justa IOCG deposit in Peru, based mostly on magnetite geochemistry, just to keep it a little shorter. So one of the main questions that we still have about IOCGs are the sources of the fluids. So we have two main hypotheses, magmatic derived hypothesis and a non-magmatic derived hypothesis for the sources, in which the heat, the metals, and the fluids are associated or not with a magma source. Some authors argue that the sources can be mixed, but we can test this hypothesis by looking at temperature proxies and isotopic fractionation associated with those. So those are the ones that we're going to focus to understand the evolution of the Mina Justa deposit. So Mina Justa is in the Andean IOA IOCG belt. And here you can see my cursor, right? Yeah. We are in coastal Peru, in between Lima and Arequipa, near the city of Nazca. And this is the region where the biggest iron oxide apatite in the country is, which is Marcona. And very close to Marcona, literally like 5 kilometers from it, is the Mina Justa IOCG deposit. So they are very close in space, and because of that, there has been it has been hypothesized that they are related in time or genetically related. And so this area in general, this belt, is a really good district to study because it's the youngest IOCG IOA belt, and so it has seen way less metamorphism or deformation events compared to the deposits, let's say in Australia or in Brazil. So we can most clearly see the original signatures in the isotopes and the composition of the minerals to better understand how these deposits formed. So now very quickly, I'm going to show this clip about the Mina Justa geology. Mina Justa is hosted in a volcanic sedimentary sequence called the Rio Grande Formation, and that is here in the blues and greens. And mineralization is mostly concentrated in the mantos, which are these purple features, and the hydrothermal unit, that's how the mine geos call it, that is the red thing. The hydrothermal unit is the one that contains most of the sulfide mineralization, but magnetite, it occurs both in the mantos and the hydrothermal unit. So we sampled core that intersected both of these to compare the textural and the composition for both mineralization styles. And the mineralization consists mostly of chalcopyrite, bornal, and chalcocite. Now, when looking into the magnetite itself, we can divide it into magnetite from the manto and magnetite from the hydrothermal unit. Magnetite from the manto, I identified like 3 main types, let's say. The first one is the inclusion-rich magnetite, which is the one encircled in red. And so in these backscatter images, we can see that this inclusion-rich magnetite is a little darker. But we also see some magnetite that is dark but has no visible inclusions, like in these bands in here. And then we see what I call bright magnetite, that is just magnetite that looks bright in backscatter. And these differences in brightness in backscatter can be translated into different concentrations of trace elements. Additionally, in the magnetite from the mantle, we can see some musketovite, that is hematite that has been replaced by magnetite, but preserving the original crystal structure. And we also see triple junctions in grain boundaries, which are pretty typical of hydrothermal dissolution reprecipitation processes. So some of these textures you saw in El Laco as well, or have been seen in Los Corrados. So they're pretty common of IOA systems. On the other hand, magnetite from the hydrothermal unit lacks this type I or type inclusion rich magnetite, but we still see these bands or zones of bright magnetite versus dark magnetite, like in these grains. Sometimes we only see bright magnetite, so this has no zonation at all. We still see some musketovite in the hydrothermal unit, and these darker areas in the musketovite are not inclusions, they are pores. And sometimes those pores have scheelite. So some similarities, some differences. We've seen these musketovite being very common in other IOCG systems. And so based on these differences in brightness, then we looked at the composition of the different types in the microprobe. And we can see here that indeed the magnetite that has inclusions, or that is of the dark type, has less iron content, which means that that iron has to be replaced by other elements. So here we can see that the inclusion rich magnetite as well as the dark magnetite are enriched in elements like calcium or titanium or magnesium with respect to the bright magnetite. Additionally, the composition of the manto magnetite, it's clearly different from the composition of the hydrothermal unit magnetite because of an overall enrichment in chromium, manganese, nickel, and vanadium, which are really compatible elements in magnetite and indicate that there is a significant distinction between these two types of magnetite. So now, in order to assess the temperature of mineralization, we're going to focus on the magnesium content. And as Jose Tomas mentioned earlier, Canelo and Lacour developed an empirical geothermometer based on the magnesium content in magnetite. And so we can translate the content of these elements in magnetite into temperature. And so here we have applied that linear correlation, and we can see that indeed the magnetite that is inclusion rich formed at way higher temperatures compared to the other types, and also that the magnetite that I call dark, it also formed at a higher temperature than the bright magnetite. And so overall, these temperatures are pretty high, and so they are consistent with a source that is magma derived. Now, to kind of verify that, we're going to look at the isotopic fractionation of the fluids associated with mineralization to see if they indeed follow a lower fractionation trend associated with high temperature fluids. So in this slide compiled by these authors, there's data for magnetite from different deposits as well as magnetite from igneous rocks. And the variations in these delta 18 versus delta 56 iron plot indicate the processes in which magnetite has been going through. And so everything that falls within this orange box has been classified and verified as being of magmatic or high temperature hydrothermal origin. So now I'm going to zoom into this box into this diagram. So here is the same diagram as before, but zoom into the what we call orthomagmatic magnetite region. And I'm also going to show data about the oxygen composition in terms of delta 18 versus cap delta 17 data. And so what this extra analysis gives us is the involvement or not of oxygen sources into magnetite that cannot be discriminated just by looking at the delta 18. So again, here, everything that falls within the dashed boxes is interpreted to be magmatic or high temperature hydrothermal magnetite. So now in the left, we see that almost all the data from Mina Justa plot within the igneous or magmatic high temperature hydrothermal magnetite. And the data is very similar to the distribution that we see from the Candelaria IOCG deposit. So this is telling us that the iron and the oxygen is being sourced from a magmatic source, and that is in agreement with the high temperatures that we see. Additionally, in the plot on the right, we see that the data from Mina Justa plot within or very close to what is interpreted to be magmatic or hydrothermal high temperature magnetite. In this plot, these are fields that were calculated by Peters et al. Indicate the regions in which magnetite should fall if the fluids had equilibrated with either seawater or meteoric water or brines. So because we don't see any of our data plotting near or within these other fields, then we can say that the oxygen that was in the fluid from which magnetite precipitated did not have any contribution from any of these other water reservoirs or oxygen reservoirs. So with this, we have corroborated that indeed we have an isotopic fractionation that is in agreement with the temperature, and we have also
okay, I'll be there now. Can you dial 00436?
Oops. Okay. And we have also corroborated the source of the metals, in this case the iron, and the fluids, the oxygen, by this isotopic analysis. So to summarize this part, we've seen that fluids and ore sources at Mina Justa are of magmatic hydrothermal origin. And then by comparing these with the magnetite textures of the mantle versus the hydrothermal unit, and seeing that there is a very close spatial association with Marcona, can we say that Mina Justa indeed has like two different parts, like an IOA that formed first and then was overprinted by an IOCG? So to know this, a way that we can test this hypothesis is by determining the duration and timing of iron versus copper mineralization. And so now I'm just going to show very briefly what we have been doing in terms of this part of the geochron work. About a decade ago, Chen et al. Did a very holistic study about this district, the Marcona Mina Justa district, and he got ages for the Marcona deposit of about between 170 and 150, and for Mina Justa copper mineralization between 99 and 95 million years. However, all this data was done with like argon on feldspars or micas, so a little bit on amphiboles. And for the sulfide mineralization in Mina Justa, what he actually dated were feldspar envelopes, and he dated those with argon. So when looking very carefully at the samples that were dated by these methods, we cannot really assess the copper mineralization by what was actually dated. So the data that he got is plotted here first with these little dots. And these are microcline points. And this was on actinolite. Now, what we've seen with our work in progress about the geochronology is we used uranium lead in situ laser ablation analysis on titanite, magnetite, and apatite to constrain the timing of the iron mineralization at Mina Justa. And surprisingly, for both the mantle and the hydrothermal unit, everything is way older than what the copper mineralization at Mina Justa is supposed to be. So none of our data yield magnetite mineralization younger than like 140. The titanite data indicates that there was at least one regional hydrothermal event that affected both Marcona and Mina Justa around 160. The apatite show a little more variability, but coupled with the titanite data indicates that this was a very long-lived system overall. Even though the magnetite data, this is still exploratory work because we're still developing the standard, the results are exciting because they also agree with a long-lived magmatic hydrothermal history or like multiple pulses involved in this district. It also indicates that the magnetite from the mantle and the hydrothermal unit could be coeval and that they could also correspond with the same event that formed the giant Marcona IOA mantos. So in order to just summarize that, now we can say that if we think that Marcona and Mina Justa were indeed coeval, at least the magnetite events, then the fluid sources, both at Mina Justa and at Marcona, should be of magmatic hydrothermal origin. And then if the Marcona and Mina Justa magnetite mineralization are contemporaneous, then is sulfide mineralization younger? We think it's probably younger, but how much younger? We are doing some rhenium osmium geochron on the sulfides at Mina Justa, and so that's work in progress. So we still don't know, but I think really the main question is, and coming back to some of the comments that Irene was saying previously, is are IOCGs really IOs that just have been overprinted by pulse or pulses of CG or SG? In the case of Mina Justa, it's actually an iron oxide silver gold deposit. So which are really the main indications that we can think, or the main conditions that really result in IOCGs versus having just IOs? And so, yeah, with that, here are the references that I used, and I'm happy to hear any comments or answer any questions. Thank you.